Good afternoon. I am Preeti Shrivastava from Sri Shankaracharya Mahavidyalaya, Junwani. Today's my topic is modulus from paper 1 abstract algebra. Here, what is R modulus? R be a ring. A left R module M consists of an abelian group M with operation plus. Then there is a mapping dot R cross M to M such that for all R and S in belongs to R and X comma Y belongs to M. Then there are four properties satisfied, that is called R module left R module M. There is R dot X plus Y is equal to R dot X plus R dot Y. Then R plus S dot X equal to R dot X plus R dot S. R dot S multiplied by X. Then change the brackets, R in bracket S dot X. The next 1 dot X is equal to X. Similarly, M is called a right R module if except the ring acts on the right side. Then next, what is submodulus? Suppose M be the left R modules and N is the subgroup of M. Then N is called submodulus. It satisfies two properties. A belongs to N, B belongs to N implies A minus B belongs to N, and R is a member of ring. A is member of N implies R dot A is also belongs to N. That means N is called submodulus. Next, homomorphism of modulus. M and N be a 2R modulus, then mapping F from M to N is said to be homomorphism. It satisfies two property. F of M plus N is equal to F of M plus F of N for all M comma N belongs to M. Second one is R is a member of ring, M is a member of M. Then F of R dot M equal to R dot F of M. Next, isomorphism of modulus. F is a mapping from M to N. Here M and R2R modulus is called isomorphism if F is 1 1 on 2. Then F is homomorphism. On the other way, F is 1 1 on 2 and F of M plus N is equal to F of M plus F of N. F of R dot M is equal to R F of M, where is R is a member from ring, M is member of modulus. What is the kernel of the homomorphism? F is a mapping from M to N be a R homomorphism of R modulus. Then it means kernel F is equal to X belongs to M such that F of X is equal to 0. Finitely generated modulus. R modulus M is said to be finitely generated if there exist n elements A1, A2 up to An which is belongs to M such that it small m is any member of capital M. It's written as M equal to R1A1 plus R2A2 up to Rn where all Ri's belongs to ring R. Let us see the theorems. Theorem statement is if M be the R modulus X belongs to M, then R dot X, which is the set represent R into X such that R belongs to R, is a submodulus of M. Here we have to show that R dot X is a submodulus of M. That means we have to show that R dot X satisfy two properties. A minus B belongs to R dot X. Second, R dot A belongs to R dot X. These two properties satisfied, then R dot X is a submodulus. Let us consider A comma B belongs to R dot X be the arbitrary element. Then by the definition given in the question, A equal to R1x, B equal to R2x, where R1, R2 belongs to ring. Firstly, we shall show that A minus B belongs to R into X. Let us consider the left hand side, A minus B. Put in the value A equal to R1x and B equal to R2x. Because R1 and R2 are the member of ring, we have R1 minus R2 dot x, which is also belongs to R dot x, which represent in the also question. Then A minus B belongs to R dot x. Let us consider the second. R belongs to R and A belongs to R dot x. Then A equal to R1 dot x. Then left hand side R dot A is equal to R. Then we put the value of A R1 dot x equal to R1 dot x is also belongs to Rx. Hence Rx is a submodulus. Then next theorem. Let Ni, where I belongs to index set, be the family of R modulus of an R modulus M, then intersection of all Ni is also an R submodulus. Then given in the theorem N1, N2, N3 up to so on are submodulus, then we have to show that intersection of N1, N2 up to N terms is also a submodulus. Then let us consider a family of submodulus. Then we have to show that intersection is also our submodulus. Let's begin. X comma y belongs to intersection of Ni and R is a member of ring. Then X and Y is compulsory in each member of Ni, N1, N2 up to so on. That means we remove the intersection sign, then we use the symbol for all I belongs to index set. Then every Ni is a submodulus, then it satisfies two property. That means X minus Y belongs to Ni and R comma R dot X belongs to Ni for all I belongs to index set. Then we remove the sign of for all I belongs to index set. We put intersection both properties. X minus Y belongs to intersection of Ni where I belongs to index set and R comma X belongs to intersection of Ni where I belongs to index set. Hence intersection of Ni is a R submodulus, hence proved. Then next theorem. Prove that the kernel of F is a R submodulus. Let X comma Y belongs to kernel F be the any two arbitrary element, then the by definition of kernel F, F of X equal to 0, F of Y equal to 0. Then kernel F is we have to show that kernel F is a submodulus, then it also satisfies the two properties. X minus Y belongs to kernel F. Second one is R dot X belongs to kernel F. Let's start. First left hand side F of X minus Y equal to F of X minus F of Y equal to, because image of any element belongs to kernel F is become a 0. That's why F of X 0 minus F of Y ki Y values 0. Then it implies F of X minus Y become a 0. X minus Y image is also 0. Then X minus Y is also belongs to kernel F. Second one. R is a member of ring. Then F of R dot X is equal to R F of X. Because X is a member of kernel F, then its image is 0. R dot 0 is equal to 0, then R dot X is also belongs to kernel F. That's proof F kernel F is a submodulus. Then next is fundamental theorem of R modulus. Most important theorem in modulus. Here is the statement M and N are two modulus, R modulus. If mapping F is a mapping from M to N homomorphism with kernel K, then we have to show that M upon kernel F is isomorphic to F of M, or M by K isomorphic to N. Let's begin a proof. Then given that F is a mapping from M to N is homomorphism, and by the definition of kernel F we know that X belongs to M such that F of X equal to 0. Then we have to show that M by kernel F is isomorphic to F of M. Let's define a mapping phi M upon kernel F tends to F of M such that phi of X plus kernel F equal to F of X for all X belongs to M. Then we define a mapping. Firstly, we have to show that our mapping is well defined. Then we have to show that it's isomorphic. Let's begin. Phi is well defined. We consider a two element of kernel M upon kernel F. X plus kernel F equal to Y plus kernel F implies X minus Y belongs to kernel F. Then any member belongs to kernel F, then by the definition of kernel F, image is 0. Then we have F of X minus Y equal to 0 because F is a homomorphism. Then properties of F of A minus B equal to F of A minus F of B. Then we have F of X minus F of Y equal to 0. Then we get F of X equal to F of Y. Then we consider the mapping. We put the values of F of X and F of Y. That is phi of X plus kernel F equal to phi of Y plus kernel F. The mapping is well defined. Then we start our mapping, shows that our mapping is well defined. Then we start the show it is isomorphic. Let's begin. Phi is 1 1. Phi is 1 1 shows phi X plus kernel F is equal to phi Y plus kernel F. Then by the definition we define the mapping. Its image F of X equal to its image F of Y. Then F of X minus F of Y equal to 0. Then by the definition given in theorem, F of X minus Y equal to 0. Then image of any element is 0 belongs to kernel F. Then X minus Y belongs to kernel F. That means X plus kernel F is equal to Y plus kernel F. This is phi is 1 1 proved. Then phi is on to phi of X plus kernel F equal to F of X. Since F is homomorphism, then F is on to. Then it is also shows that phi is also on to. Then last we have to show that phi is homomorphic. We consider phi of kernel F plus X plus kernel F plus Y. Then next phi of kernel F plus bracket X plus Y. Then by the definition we defined in mapping F of X plus Y. Then since F is homomorphism, image separated F of X plus F of Y. Then we put the values of F of X and F of Y. Phi of kernel F plus X plus phi of kernel F plus Y. This is the proof of phi is homomorphic. Then hence proof M upon kernel F is isomorphic to F of M. And thank you so much.